Alright, in this video we're going to be working AP Pre-Cal Homework 3.1, which is about rational functions and mostly about their zeros and their vertical asymptotes and possible holes in the graph. Okay, so we're going to start off with r of x equals g of x over f of x, find the domain. Okay, so this is a pretty direct line of questioning, type of which you will definitely see on the unit test when that comes up. So I think what I'm going to do, I'm just going to write out r of x. I'm going to need a thicker pen. Alright, so being g divided by f, that's going to be x squared plus 3x minus 18 divided by f, which is x to the 3 plus 2x to the 2 minus 35x. All right, so we're going to find the domain. And if we want to find the domain, we're just going to need to exclude any x value that causes r to divide by 0, so any zeros of the denominator. So I'm going to grab that denominator and say, all right, x to the third plus 2x squared minus 35x. That needs to equal 0. So we're going to solve that by factoring. X times x squared plus 2x minus 35, that's going to equal 0. Then I'm going to factor the thing in parentheses, and I think that's going to be x plus 7x minus 5, yeah. So these zeros of the denominator, x equals 0, x equals negative 7, and x equals 5. Okay, so these are the x values we need to exclude from the domain. So the domain is going to be all x except for 0, negative 7, and positive 5. Okay. The zeros of the numerator, those are going to be the zeros of r. Okay, provided that they're not also zeros of the denominator. I'm not sure. No, I don't think so. No, neither of those are factors. Okay, but on the question that we're going to ask you on the test is multiple choice, right? And they're going to give you those numerator zeros as answer choices, or maybe some of them. And so you need to know that the domain excludes only zeros of the denominator. All right. Okay, so an example of a rational function that has a 0 at x equals 1. All right, so the zeros, those are going to go in the numerator. So this rational function, okay, if it's a rational function, it's going to be a fraction. Put in a fraction bar. Okay, the zeros, they go in the numerator, so it's going to be x equals 1. That would make x minus 1 equal to 0. A whole at x equals 2. Well, we get a whole when we've got the same factor on top and bottom. And then a vertical asymptote at x equals 3. A vertical asymptote is going to be a 0 of the denominator that's not also a 0 of the numerator. And that would be x minus 3. Okay, so that one will go in the denominator only. And this is an example of a rational function, right? We don't need to worry about any leading coefficients or anything that fits the description. We're good. Let's move on. All right, so now we've got this prompt. So let f be a rational function. Okay, and I definitely included this space intentionally so that we could do some work on trying to figure out what it is. So the numerator, or the polynomial in the numerator of f, so I'm going to say, all right, f is a rational function, so it's going to be a fraction. Polynomial in the numerator has a 0 at x equals 2. Does not have a 0 at x equals 1. Okay, so I'm not going to put x minus 1 in there. Polynomial in the denominator of f has zeros at x equals 2 and at, you can't see this, but x equals 1. Okay, so read this again. Okay. Oh, okay, yeah, that's fine. Polynomial in the denominator does have a 0 at x equals 1. Multiplicities of the zeros at x equals 2 in the numerator and the denominator are equal, so we'll just assume they're 1. Determine whether each statement is true, false, or cannot be determined from the information given. F has a whole at x equals 1. That must be false because they said that the numerator does not have a 0 at x equals 1. Okay, B has a whole at x equals 2. That must be true because they said that the multiplicities of the zeros at x equals 2 in the numerator and denominator are equal. Okay, so if we know if they have equal multiplicity, that's going to completely cancel off, and that will cause a hole in the graph. Okay, f has a vertical asymptote at x equals 1. Yes, that must be true. And f has a vertical asymptote at x equals 2. That one must be false. Because we know there's a hole there because of the statement about the multiplicities of the zeros at x equals 2 and the numerator and denominator being equal. Okay, so I think that's all for that one. All right, now number 4. So this is where we're going to consider the graph of y equals x to the a times x minus 2 divided by x to the b times x plus 3. A and b are real numbers. I think probably, we're just going to be considering the cases where they're positive whole numbers, but if a is 3 and b equals 0, I guess it would have been nice if I'd put negatives on those and maybe do a little bit of negative exponent work, but something for the future. So a equals 3 and b equals 3. Okay, I think for this time, or maybe for all of them, I'm going to actually write out what we've got here. X to the 3 times x minus 2 divided by x to the 3 times x plus 3. Okay, that would be the graph that we're looking at. Okay, so near x equals 0, well, we're going to be able to cancel off all 3 powers of x. Okay, and not be left with any in the numerator or denominator. So if all of them cancel, and it's even multiplicity on top and bottom, like we were saying on the previous problem, there's going to be a hole in the graph. If a equals 4 and b equals 5, if I went and canceled, okay, I could cancel off 4 powers, okay, which would leave me with 1 in the denominator. So that would be x minus 2 over x times x plus 3. And any zero of the denominator that's left after canceling everything, after simplifying, that's going to be a vertical asymptote. So since there was an extra factor of x in the denominator, that made the graph have a vertical asymptote near x equals 0. A equals 7 and b equals 6, so the degree of x in the numerator exceeds the degree of x in the denominator. Describe the behavior of the graph near x equals 0. Okay, kind of the same idea here as the other one. All but one of the x's will cancel off. Okay, so I'll be left with an x in the numerator this time. So x times x minus 2 over x plus 3. Okay, now these are only equal provided that x is not equal to 0. Okay, but if x is equal to 0, okay, we're going to have a hole in the graph. Okay, and the result of that extra factor of x being in the numerator is the thing on the right of the equals. That's what we would use to find the y-coordinate of the hole. Okay, or maybe a more simple way to find the y-coordinate of any point on the graph, but most useful for finding the y-coordinate of the hole in the graph. So we would plug in x equals 0 there, and we would see that y would equal 0. So that just means that we have a hole, and we can actually say that the point is where x equals 0 and y equals 0. That's just the impact, is that the hole becomes on the x-axis. All right, number 5. The rational function g is given by g of x equals 2 over x minus 4 minus 3 over x minus 5. For what input values of g are the output values of g equal to 0? Okay, that's kind of a different wording, right? Like that's kind of weird. Didn't just come up with that on my own. I definitely we brought that in from somewhere. Thought you might need to be familiar with that wording. Okay, so for what input values? Well, input is like x, which is g of x. What x makes the output values of g, okay, so it makes g equal to 0. So what we're doing is we're finding the zeros of the function. Okay? I think that, for most of us, that's going to be, what we would expect we're going to do. I just want to be really clear about that wording, because that's, it's not a wording I've used before. Okay, so we've said solve the equation g of x equals 0, find the zeros of g, find the x-intercepts, all sorts of things kind of similar to this, but not exactly. So what x makes g equal to 0? So we're going to take the formula and we're going to set it equal to 0, and we're going to solve. So that's 2 over x minus 4 minus 3 over x minus 5. And we need that to equal 0, but I'm actually going to leave a little bit more room. Zoom in a little bit more. Yeah. All right, Now, if we're going to keep going, we're probably going to need to get a common denominator. Now, it's not the only way you could solve this problem, and if you've got a different way, you can go ahead and do that. What I'm going to do is I'm going to multiply by the opposite denominator on top and bottom. So x minus 4 divided by x minus 4. And over here, I'm going to multiply by x minus 5 over x minus 5. It's going to be hard for you to see that, but I'll get that on screen in a second. See, maybe I can drag that over. Okay, that's as good as I can get. Okay, now, yeah, because that's on the very left edge of the page. That was a mistake. All right, there we go. So when I multiply these things out, I'll probably need some parentheses on these two. Okay, I'll have 2 times x minus 5 is going to be 2x minus 10. Minus, and then distributing the 3 over the x minus 4, I'll have 3x minus 12. And then on the denominator, I'll have an x minus 5 times x minus 4. When I go to combine these with a single denominator, of x minus 5, x minus 4, I'll be subtracting 2x minus 10 minus all of 3x minus 12. So we need to throw that in parentheses. And then we're going to, okay, I've run out of room. Let's see if I can make myself some more room here. All right, so we can keep going, and we're going to distribute the negative. So 2x minus 10 minus 3x plus 12. All divided by still x minus 5, x minus 4. And I'm not going to bother to distribute this out because the denominator is not going to really impact my zeros. In fact, it might actually stand in the way. If I was able to like cancel off a factor, I would know that that would not correspond to a 0 because the original function would be undefined. So I'm going to leave it unfactored in the denominator. So 2x minus 3x is a negative x. Negative 10 plus 12 is positive 2 divided by x minus 5 times x minus 4. And if we're looking for the zeros of this function, which I've now rewritten with a common denominator, I'm going to be looking for the zeros of the numerator. So I'm going to be saying, all right, negative x plus 2 needs to equal 0. And that happens when x is equal to positive 2. Okay, so that's going to be the input value. That's going to be the only input value that makes the output value of g equal to 0. Hey, now number 6, I really like this problem. This is the type of problem that we're going to be bringing back to you repeatedly throughout this unit. We're going to give you two graphs, and we're going to talk about these rational functions, which is just like this graph divided by the other graph, or the other graph divided by the one graph. And so the graphs of polynomials f and g are shown in the figure below. So we know they're polynomials. And so certain things about the zeros and their multiplicities we'll know are true. Okay, a is going to be f divided by g, and b is going to be g divided by f. All right, so the behavior of the graph of a at x equals 1. All right, so a, which is f divided by g, I'm just going to double check that, yeah, make sure I don't do all of them the wrong way. F divided by g. All right, at x equals 1, what's happening to f? At x equals 1, f is going towards 0. And at x equals 1, I mean, I've got to assume the g is going to be negative, right? Looks like a third degree polynomial, looks like it's going down forever. 0 divided by a negative number, that's going to equal 0. Okay, so I'm going to say that a has a 0 at x equals 1. Describe the behavior of the graph of a at x equals 2. So a is f divided by g. And at x equals 2, f is a positive number. So I'm looking at the graph right there. And so I've got positive divided by g of 2 is equal to 0. And so if I've got a positive number divided by 0, that's going to be a vertical asymptote. A 0 of the denominator that's not also a 0 of the numerator. Right, describe the behavior of the graph of a at x equals 3. A is still f divided by g, which is going to be going towards, okay, at x equals 3, f is equal to 0, and g is equal to 0. And both of these things are on the x-axis. Moreover, they're both single roots. And that's going to be important, right? Because we know that the multiplicities are equal. So since they're both zeros there, I'm going to say, all right, I'm going towards 0 divided by 0. And that's oftentimes a sign of a whole. But since it was 0 with multiplicity 1, that is going to be, on top and bottom, that's going to be a whole. And I know that those were multiplicity 1 because the graph was passing through those zeros confidently. Not hesitating, there wasn't a point of inflection on the graph at the 0. All right, and the last one for function a is going to be describe the behavior at x equals 4. All right, at x equals 4, f is having a double root, at least. Okay, but I know it's an even multiplicity root, so I know the multiplicity is greater than 1. So I'm just going to assume it's 2 for the sake of the problem. And then g is also equal to 0, but it's having a single root at x equals 4. So I'm going to say, all right, well, f was having a double root, so I'm going to, say it's like that. And I'm not going to write in like, oh, I'm canceling off those zeros, because that's not legitimate. 0 divided by 0 is not equal to 1. Okay, but the extra value of 0 in the numerator after canceling would cause the y coordinate of the whole to be at y equals 0. So I'm just going to say this is also a whole, but at the point where x is 4 and y is 0. So it's a whole on the x-axis. All right, now we're going to talk about b. So b is g divided by f. Okay, so at x equals 1, okay, a went to 0 over a negative number, so b is going to go to a negative number over 0. That's going to be a vertical asymptote. Okay, b at x equals 2. At x equals 2, I had positive over 0. I'm going to now, because b is g over f, I'm going to have 0 over positive. I mean, we could go back in and look at the graphs again, but this problem is somewhat repetitive, and we're going to kind of solve it the same way every time. So I'm just going to point out that since g over f is the reciprocal of f over g, I'm just going to kind of take the results from a, b, c, and d and apply them to e, f, g, and h. All right, so 0 over a positive number, that's going to give me a 0. At x equals 3, let's see what happened there. 0 over 0, but single root on top and single root on bottom, that's just going to be a whole. We're not going to have enough information to determine the y-coordinate of the whole. We could say it's at x equals 3, but it's describing the behavior of the graph of b at x equals 3, there's a whole. So at x equals 4, okay, we saw that there was at least a double root of f, so that's going to be a double root in the denominator and a single root in the numerator. And so what that would mean is that after canceling off that common factor of x minus 4, I would have still an extra factor in the denominator. So after canceling, it's still a 0 of the denominator. That's a vertical asymptote. All right, now we've got ourselves a picture of the graph of f of x, which is x plus a over x plus a times x minus b times x plus b. Okay, so what are the values of a and b? All right, well, a is going to be something I can find by, looking at the whole, right? Because I've got the same factor on top and bottom. So let's say that x plus a is equal to 0, right? That factor is 0 at the x coordinate of the whole. So I would say at x equals negative 2. So negative 2 plus a is equal to 0, and a is equal to 2. Then as far as b goes, I'm going to be able to find that after canceling the factors of the denominator. Okay, so that's x minus b and x plus b. So I'm seeing negative 3 and 3. Okay, so b must be 3, right? Yeah, x minus 3, x plus 3, that would give me vertical asymptotes at x equals 3 and negative 3. Okay, so now because of this, I'm going to just say x minus b equals 0 at x equals 3. So that means b equals 3. Okay. I suppose b could have been -3 as well, and there wouldn't have been anything wrong with that. All right. Then what is the exact location of the hole? Use limit notation to display my answer. Okay, so if I go back to the original statement of f, and I thought about what happened after I canceled off the common factors, I would have this is equal to 1 over x minus 3 times x plus 3. So that's 1 over x squared minus 9. Just as long as x was not equal to what? -2. Okay, so the exact location of the hole is going to be, okay, so the limit of f of x, I'm not going to copy that original expression, as x approaches -2. When x is getting closer and closer to -2 from each side, y is approaching, well, whatever the simplified expression would approach. All right, so that's going to equal the limit as x approaches -2 of 1 over x squared minus 9. And we're going to try plugging in, right? If we had tried plugging in -2 originally, knowing that a was 2, we'd have gotten 0 over 0, and that's an inconclusive answer. That's not a real number. But this is not going to give us 0 over 0. It's going to give us 1 divided by -2 squared. Okay, so I'm going to square it, multiply it by itself. -2 times -2, that's positive 4, minus, a little ahead of myself, 9, and that's going to be 1 over -5, or -1/5. And limit notation to display my answer, that's the exact y coordinate. Yeah, I'm just going to leave it at that. All right, number 8. G of x is equal to 3 times x plus a over x plus a times x plus b. Okay, which means that the x plus a's are going to be canceling. Okay, we're going to do the same thing. The canceled values of a, I think I used blue for that last time. Fortunately, vertical asymptote appears to be in blue, but it's more teal. Anyway, the x plus a is going to equal 0 at the x coordinate of the hole. So 6 plus a equals 0, a equals -6. Okay, and then in order to find b, that's going to be revealed to me using the vertical asymptote, because that's the leftover factor in the denominator. Okay, I know that the denominator is equal to 0 when x equals -2. So -2 plus b equals 0, b equals +2. So those values of a and b. What's the exact location of the hole? Use limit notation to display my answer. Okay, we're just going to do the same thing as before. If we cancel this thing off, g of x is equal to 3, that's all that was left within the numerator, over x plus b was 2, so x plus 2. And we're just going to say with a hole at x equals +6. Right, so the limit of g of x, no, pardon me, that's not where that goes. The limit of g of x, start drawing in my arrows, the y coordinate that g is approaching, that closer x gets to 6, that's going to be the equal to the limit as x approaches 6 of the simplified fraction 3 over x plus 2. If I were to try plugging in on that, I would get 3 over 6 plus 2. And we would simplify that and say that's equal to 3/8. Try it on screen, but I think it'll fit right there. Yep, there we go. All right, now this next one has got a table of values, and I missed a negative. So we're definitely going to want to, make sure we change that. Otherwise, this problem would probably make very little sense. Okay, that's a huge mistake, but the ink is dry on those copies if you're looking at it at home. So my apologies. Okay, but if you're looking at this for the first time, there you go. That's going to be negative 0.502 at 4.01. What is the domain of f? Okay, well, it's everywhere that doesn't cause the denominator to equal 0. So x is not going to be able to equal 4 because that would cause f of x to equal something divided by 0. And x is going to not be able to equal 6 because that would also cause the denominator to equal 0. What value of x does the graph of f have a hole? Okay, so I've got 2 points of discontinuity, and I kind of wish that I had added a spot here that was like 4 and does not exist or something to that effect, does not exist or undefined or something like that. And same at 6. So I'm just going to point out that at 6, this function is not going to exist either. I guess maybe when I was writing it, I thought it was like obvious by the domain, but that just would assume you understand the domain question. Okay, so f is going to have a hole at one place and a vertical asymptote somewhere else, kind of based on the numbers I'm seeing. -1, -10, -100. Those numbers are getting pretty big pretty quickly. Okay, that's evidence of a vertical asymptote. So I'm going to actually answer C first. I'm going to say, all right, well, it looks like the vertical asymptote is happening at x equals 6 because the numbers are getting big. Okay, the hole is probably going to be at x equals 4. Okay, so that means, okay, A is going to equal 4. And I see that's question D, so there you can see it, but I just answer it right there. Because as soon as I see that I'm realizing I have a hole at x equals 4, I look back up at f, and it's like x minus something over x minus 4. Something's got to cancel, so I need an x minus 4 over x minus 4 to cancel. So that means x equals 4, and that means that as a result, a equals 4. Okay, so then we found the value of a. All right, now these are something that I had not really gone into in the lesson in class. The limit from the positive side and the limit from the negative side. What I'll say is on the quiz over this, you do not have to contend with any one-sided limits. So these are the exponent of plus and minus. That's not what it's about. It's kind of like what we did earlier, was like express the location of the hole with limit notation. Okay, and so if we're looking for the limit as x approaches 4 from the positive side, I'm just going to draw you a little diagram. This is 4. As x approaches 4 from the positive side, that means this. And you saw in the graphs, I was kind of drawing 2 arrows. I'm just going to give you that diagram. And then approaching from the negative side, well, over here is where x is negative. So I'm going to say that's what we mean by the negative side. And then I'm going to say this is x approaching 4 from the negative side, which means from the left. It's a left-hand limit, and in blue we're talking about a right-hand limit. All right, so from the positive side, it's asking what's happening with f of x. Okay, so that's going to be thinking about 4.1 and 4.01, and what am I getting closer to? Well, it looks like I'm getting closer to 0.5, without any other, also, I mean, being honest, I'm looking to the left of x equals 4 as well, but it looks like that's probably what they're getting at. It would be believable to say that the limit could be 0.5. And then the limit from the left, as x approaches 4 from the negative side, right here, looks like the same thing. Oh, it's supposed to be negative half. Okay, I made the same mistake again. Okay, but I can fix that pretty easily. Let's say that was going to be negative 0.5, and this one is also approaching negative 0.5. So at the location of a hole in the graph that's caused by, canceled factors, we're going to see the one-sided limits both agreeing. That's a fact that you're going to be noticing in this class. All right, now as we approach 6 from the positive side, okay, that's from the right, numbers that are greater than 6, I'm seeing the values are increasing. Okay, and I know that there's a vertical asymptote there, so that means the numbers are increasing without bound. They're going to positive infinity. And then as I approach from the left, the numbers are getting more and more negative. -1, -10, -100. I know it's vertical asymptote. That means that I've got to be approaching negative infinity from the left. Okay, so we're going to go over here, but that whole thing about determining which infinity we're approaching at a vertical asymptote, that's really part of the lesson next time. So we're getting you ready for that. Okay, so as x approached 6 from the positive side, the output values of f in the table were positive and getting larger. So I'm going to say that approached positive infinity. And then this limit down here, this one approached negative infinity because the output values of f to the left of x equals 6 were negative and getting more negative. -1, -10, -100 versus over here to the right, 10 and 100. Okay. All right, now the last one here. Now this is one, I remember I put this one at the back of the homework because I figured that I just wanted to, reward anybody that went in, did all the problems, and give you one that was really, really close to one that was the problem that's on the quiz. So consider h of x equals 2x squared minus 7x minus 15 over x squared minus 6x plus 5. Okay, if it's not factored for us already, we're going to need to factor it. So the denominator looks easier to factor than the numerator to me, so I'm going to start with that. Okay, so factors of 5, it's got to be 5 and 1. If it adds to -6, that would be -5 and -1. Okay. In the numerator, I'm going to be looking for two numbers that multiply to 2 times -15 is -30. So I'm looking for u times v equals -30, while adding up to -7. Okay, so that's going to be 10 and 3. I think it's going to be -10, +3. So I'm going to split up. I'm going to actually do this factoring work off to the side. 2x squared minus 10x plus 3x minus 15. So I factor out the 2x, I got an x minus 5, plus 3 times x minus 5. Okay, then I factor out the x minus 5s, there we go, and I'm left with a 2x and a +3. Okay. Now I see that common factor of x minus 5 on top and bottom, so I'm going to cancel that off. Find the vertical asymptotes of the graph of h. Okay, these are the values, the zeros of the denominator that are left after the cancellation. So that's going to be x equals 1, because x minus 1 is all I'm left with in the denominator. Find the xy coordinates of any hole in the graph of h. Well, that's going to come from anything that I canceled. Okay, the 0 of the factor that I canceled is x equals 5. So I'm going to say, all right, well, x equals 5. And then the y coordinate I'm going to get by plugging into the expression for h that's simplified, what's left after the canceling. Okay, so I'm going to say, in fact, I think I'm going to get rid of the factoring work. All right, so that's much better. So now I'm going to plug y into the simplified expression. So wherever I see x in the new formula, I'm going to plug in 5. So y is 2 times 5 plus 3 over 5 minus 1. Okay, so that's going to be 13 divided by 4. So I found the x coordinate and the y coordinate. I'm ready to move on. Okay, find the zeros of h. Okay, that's going to be the zeros of the numerator after canceling. Okay, so I'm going to take that 2x plus 3, I'm going to set it equal to 0. 2x plus 3 is equal to 0 when 2x equals -3. I'll divide both sides by 2, and I'll get x equals -3/2. Right, and that's going to be all for this problem set. So thanks for watching. Hope this helped.